Okay, here we go. Have a look. So how about this one? If we're going to see, yes, yeah. So if you're going to, we want to see here how like the space jumpers climbed this big 694 meter high TV antenna. Mass including gear is 154 kilograms. So we want to know how much is this tower going to compress. Okay, if we model the tower, and you have to do this. I mean, you wouldn't have to, but it'd be difficult to find the Young's modulus for the tower. You'd have to use calculus because it would vary as a function of height. So it'd end up being a much harder problem. But a lot of times what we'll do is we'll just model, we'll find something that's reasonably close and model the complicated structure by something simpler. Like in this case, a steel cylinder, 12.5 centimeters in radius, height of the tower. Okay, so what do? What's our equation here for Young's, for compression or tension or compression, within the elastic limits, which is this clearly is. So how does that work? Remember? So F equals what?
Force times area.
So it's Young's modulus
That's one. Okay.
times area divided by
Delta L.
by L naught times delta L. So that way, these are the variables, and that's K, right? That's the spring constant. I mean, if you thought of it as a spring, right? Okay, so we want to know what delta L is. So we're going to solve this thing for delta L. That's really all you have to do with these. These are really, they're not, they shouldn't, I mean, the numbers are a little bizarre, but really all you're doing is manipulating that one equation with this stuff, right? So if we want to find delta L, then we're just going to end up with a fraction on the other side. We're going to have force on top. We're going to have to multiply by the reciprocal, so we get initial length divided by Young's modulus times cross-sectional area, right? So let's plug this stuff in. I guess we're going to need to know what Young's modulus is for steel. So if we go to the reading, and I think I can actually just go back a couple pages. I've got it on here, right there. So for steel, oh, that's right, 210. That's right. We knew that. 210 times 10 to the ninth. So let's pull up the calculator and just plug these in, see what we get. That sounds like pretty much rain.
It's freezing rain right now.
Is it really? I don't think there's gonna be school tomorrow.
I don't think there's going to be school tomorrow either.
I was excited for a second.
For a split second, I got you.
Yeah. Actually upsetting.
There is no school tomorrow?
Okay, so what do we put in for force? What's the compression force here?
Force of the base jumper?
Yeah, his weight, right? So just 154 times 9.8. Okay, so we've got the quantity 154 times 9, oops, 0.8, okay, times the length, and what was the length?
694.
694. So times the initial length, 694 meters, we're all standard units, divided by the quantity.
210 times 10 to the 9.
Okay, so 210 E9 times cross-sectional area. Well, the cross-sectional area, the diameter is 12.5 centimeters, right? So the radius is going to be 6.25 centimeters, so 0.0625 meters. So we have to do pi r squared.
Isn't 12.5 the radius?
Is it the radius? I think it's diameter.
This is radius.
Oh, it is?
In
Oh.
radius.
Oh, you know what? I wonder if I messed that up. I bet I meant to make that diameter. Did you not get the right answer on this one, though?
I didn't do it.
Oh,
Yeah, actually,
okay.
no, I didn't. No, I didn't get the right answer.
I bet that's supposed to be diameter. I probably screwed that up.
I did it.
Either way, you didn't get the right answer.
Okay, well, let's try it this way, and then we'll see if the other way works. So we get pi r squared, so that's the radius, I don't think it really is, but we'll see, times 0.125 squared gives us a pretty small amount. So it's about 1/10 of a millimeter. Okay, so if we want to enter this, let's try that, see what we get. I think I've still got this one open somewhere. Preview, no, preview, there it is. Okay, let's see what the correct response is supposed to be. Okay, so it is, okay, that's supposed to be diameter.
That makes more sense.
Yeah. Okay, so I need to change, let me change the wording on that. Because let's just see if we get that answer. If we change this to diameter, all I'd have to do is go up here and add, in my calculation, I can just add a 0.5 in front of that, right?
You'd have to put mine.
In parentheses, right, so we'll go insert parentheses 0.5 times and then I gotta go there. Yeah, that's it. Right, wasn't the answer, what was the answer point? So that's 0.0406. Oh, here it is right here. Oh, 407. Why 7?
Because I think you rounded off. No, I've run into this issue too.
I
Yeah,
kinda
sometimes
found that too.
The rounding is off on the.
Huh.
Yeah.
Really?
Yeah, sometimes when it's like the 5 is the number that's rounding, it'll round down instead of round up. Like 9.5, it'll go to 9 instead of 10.
This one definitely shouldn't have though, because that's a
I've
6.4.
noticed it when the 4 is the number of the 4, that it will round the other way. For reasons unbeknownst to me.
Yeah.